In the beginning, I would in particular highlight one particular person who was essential in conducting all that research. And without him, all of what I will show you will not exist probably. And this is Markus Schmidt, who has been a postdoc at MPI PKS. But in the meantime, he has moved to UC Berkeley as a Leopoldina postdoc fellow. To some extent, the talk today is a bit of an extension of a talk yesterday, which has questioned a bit to which extent neural network states might be superior to other methods, such as tensor networks. And as I would like to convince you in the following, I think that there is a regime, an important case, namely of non-equilibrium quantum many-body dynamics beyond one dimension, where artificial neural networks can access regimes which are otherwise inaccessible by other methods. Now, although we had already a bit of talks about non-equilibrium physics, I would nevertheless like to give a brief introduction into non-equilibrium physics. Because although on the one hand we are very much familiar with the fact that many physical settings can be described by equilibrium statistical physics, there are nevertheless very important incarnations of non-equilibrium states of matter in nature. And now I'm sorry, like there seems to be a technical issue. Sorry, I think I cannot advance the slides at the moment. Ah, now I can. Perfect. Sorry. Okay, thanks a lot. Sorry. Yeah, like in these non-equilibrium states of matter that can exist in nature over various scales. On the largest scales, that's certainly the universe itself. On much smaller scales, you can see here an image of a biological organism which can only survive upon sustaining a non-equilibrium state with its environment. Now, I don't dare to describe complex systems such as the universe or biological organisms. What I would like to focus on in the following is then non-equilibrium dynamics on much smaller scales at the quantum level. And that, to a large extent, is driven by tremendous progress on the experimental side in architectures which now go under the umbrella of quantum simulators. And in particular, what they have achieved in the recent last decade is to realize coherent dynamics of quantum matter at an unprecedented control at the quantum level. Practically, it just means that what they have achieved is to realize or have the most pristine realization of the fundamental equation of quantum mechanics, which is Schrödinger's equation. And therefore, what I would like to study in the following, not only because of the experimental progress, because I think also, obviously, due to fundamental theoretical questions, I would like to study Schrödinger's equation for many-body systems which are isolated from any environment and are therefore just experiencing coherent real-time evolution. But now there is something happening currently, and I think it's fair to say that today we are at a key turning point in both theory and experiment, and in particular that experiments are now approaching in a controlled way the coherent dynamics of quantum matter in two spatial dimensions. But on the theory side, we are facing rather severe limitations concerning numerically exact methods. So whenever we would like to describe interacting systems in two spatial dimensions in an exact way, we are lacking methods. And in particular, like we know that there are two regimes which we can describe rather well, like which is the regime of low dimensions in the context of tensor network methods, or in the limit of high dimensions using dynamical mean field theory. But both of these approaches are facing limitations in the physically relevant regime of spatial dimensions d equal 2 and d equal 3, calling for new approaches in this context. Now, sorry, now I'm again missing the slide. Ah, okay, thanks a lot. So, like, what is the challenge? Like, overall, like, you're very well familiar with that, so I'm just repeating what you probably already know. The problem, of course, is that Hilbert space is exponential, and when we try to, when we consider a generic quantum many-body state psi here, which is which you can express in some computational basis, say here on basis of spin configurations, in order to store the full information of the quantum state, you have to store exponentially many amplitudes psi of S. And without efficient compression of these amplitudes, that requires, of course, then exponential resources. And what we are trying to do here is to take a slightly different approach, that we don't even try to store these amplitudes, but only want to generate them on the fly when needed. So what we have in mind is to create some kind of machine which, with a simple input and output. Input is a spin configuration, and output is the corresponding amplitude, or a good approximation thereof. And suppose we have such a machine, we could just sample from that machine and get all the necessary information we need of our quantum state. And we don't have to store the amplitudes, and we just generate them on the fly when needed. Of course, that necessarily translates all the, translates all the complexity of quantum many-body physics into the complexity of that machine. And it's not clear a priori whether one can actually construct such a machine efficiently. And however, it turns out that we know that there are cases where this is possible. And one of these cases we have explored recently rather extensively. And these are cases where the non-equilibrium quantum dynamics can be described by what we called classical networks, which we introduced together with Markus Schmidt, that I was mentioning already before. The idea is actually conceptually rather similar to Jastrow or Hughes and Elsa wave functions that we heard about yesterday, and that is to represent the amplitudes, the output of that machine, by some effective classical Hamiltonian, where this classical Hamiltonian we obtain by some clever expansion in terms of some small parameter. So in the end, how I will be rather brief here. So what we do here is we essentially expand around some classical limits and obtain such an effective classical Hamiltonian performing some cumulant expansion, which we can then further variationally optimize to squeeze a bit more out of that. Importantly, although this is a perturbative approach, it still allows us to access regimes which are inaccessible otherwise. And here you can see a few examples, quantum 1D icing, but in particular, I would highlight the last two examples here. Here is a case where we studied the dynamics of many-body localized systems, both in 1 dimension and also in 2 dimensions. And what you can see here is that using these classical networks, we could describe the non-equilibrium dynamics quantitatively correct up to arbitrarily long time scales. On the left-hand side, you see, for instance, the entanglement growth in many-body localized systems as a function of time, and comparing exact diagonalization data, which are the symbols, and the results from our classical networks, which are the solid lines. And as you can see, they fit very well, even for astronomically large timescales. And we could then even push this to the regime of 2 dimensions, where there's no reference anymore, and we were able to still, for instance, compute entanglement dynamics here in the context of the quantum Fisher information. Another example that we were studying was the quantum link model in 2D, which is like genuinely interacting lattice gauge theory, which does not have any exactly solvable point anywhere, but it has a classical limit, and we were able to compute the non-equilibrium dynamics in this model essentially exactly in specific limits that are within this perturbative expansion. So these classical networks are fine, but they are only successful for, like, can only be applied for tailored problems. And of course, we were searching for a more general purpose ansatz. And clearly, one natural choice here is to use the idea by Giuseppe Caleo and Matthias Troyer by encoding quantum states in artificial neural networks. And in the end, we can use in principle the same formalism. We have, if you think about a feed-forward neural network, we can take as an input a spin configuration, as here, represented for 3 spins, like a spin S1, 2, and 3. Then we process our information, and in the end, the output of the neural network is then the amplitude of the wave function that we are searching for. Now, this approach has very interesting properties. In particular, what is different from these classical networks, which are just for tailored problems. Here, we know that in principle, neural networks are universal function approximators, which means in the end that in principle, any quantum state can, in principle, be encoded in a artificial neural net, provided it is sufficiently large. Now, what sufficiently large means, of course, is not clear a priori, but as I will show you, that's actually not a problem, at least at the moment. And moreover, the complexity of the resulting algorithm to study like real-time dynamics, say, is only polynomial in all the parameters such as the size of the neural net or system size and time, which makes it in principle a very powerful approach. But now it turns out that there are problems, and all the results so far in the literature about coherent dynamics show some limitation in one or the other sort, either in system size, like that you can reach maximally, or in the maximal timescales that you can reach with this approach. Here's one example from the pioneering paper by Giuseppe Caleo and Matthias Troyer, where you can already see that at short times, in some cases, you find that deviations start to form. And upon increasing the neural net, it doesn't seem to become much better. And in particular, there has been one example that I will discuss a bit more in the following, which has questioned the approach as a whole in the end, because they made the following observation. What they were doing is taking some one-dimensional Ising model, which they could also solve exactly using other methods. And they were comparing the performance to this artificial neural network dynamics. Now, when you were considering small system sizes, like 12 spins here, you see that like the black line here is the exact result. You can see that upon increasing alpha here, that means making the network larger and larger, and it should become better and better. What you achieve is that actually really the dynamics starts to converge to the exact result, and everything is fine. But now when you look at larger system sizes here on the right-hand side, like at some point you see a deviation of the neural network result compared to the exact one, the black line. And this discrepancy does not improve upon increasing the size of the neural network. So, which was posing fundamental questions about whether this approach is suitable at all or not. And what I would like to show you is the underlying reason for that, and how you can make this convergent avoid these kind of problems. And now, like, this is our final result. I will try to explain what we did in order to achieve what I'm showing here. Now, this is from our recent work with Markus that we put on the archive in December last year. And what we studied here are quantum quenches in a 2D transfer suite Ising model. So like here is the Hamiltonian. It has a spin-spin interaction and a transfer suite term. And what we did for this particular case is to initialize the system in a fully polarized state along the sigma x direction. just to have to be able to compare to some recent IPEPS data that was obtained also last year in some state-of-the-art tensor network calculation. Now, there's a lot of information here. Let me just highlight one or two aspects and guide you through this. So overall, there are many data lines here, maybe too many, but sorry for that. So you can see color-coded here various different neural network sizes of some convolutional neural network we use here as our ansatz. And you can also see IPEPS data from this work that I just mentioned, which is essentially exact data in the thermodynamic limit. And as you can see here, in the case on the left-hand side, say like that, there are some neural networks which are at some point departing from the others, but we can increase the neural network size always such that we achieve convergence here. And what you can also see is that the data up to the times that you can achieve with, that you can reach with IPEPS here, the data falls on top of each other, but what we can achieve additionally is to reach much, much longer times, almost an order of magnitude longer here than that is reachable via IPEPS. For other values of the transverse field, the results are not so much superior. I would say it's more or less like what you can reach with IPEPS, but certainly there are regimes which were here on the left-hand side where you can reach much, much longer times using the neural network approach. So how did we achieve this? And for that, I first have to discuss a bit how we essentially do time evolution with such neural network states. You can think of these neural network states as just some fancy kind of variational wave function. And whenever you have a variational wave function, you can, in order to do time evolution, you can introduce a time-dependent variational principle, which in the end maps the non-equilibrium quantum dynamics to a nonlinear classical ODE for the variational parameters, which in our case are just the network weights, which I denote here by eta k. And the equation you have to solve in the end is of the following form, that here's the change of the network weights, and the change of the network weights is obtained by measuring this correlation matrix S, which involves some operator O that is in the end conjugate to the variational wave function, to the variational parameter, the network weight. Overall, not so important. You have an ODE which you then just have to solve. And now when you solve it exactly, what this TDVP essentially does is something which is not like a global optimization that you are typically doing in machine learning. So you're trying to approximate a function globally, but rather what the TDVP does is that it gives you a prescription how to follow the minimum in the variational manifold step by step. So from one time step to the next. Now, if you do that, it can happen, and that's exactly what you see here. Because you cannot do it exactly, you have to do some Monte Carlo on that. You have to sample from that machine. It can happen at some point that two minima, local minima, come very close to each other, and in the end, at some point, you start to take the wrong, you follow the wrong one, and that's. Once you take the wrong one, you're out of the game because you're not optimizing globally. You're just following that particular local minimum. You don't know whether it's global or local. And that's exactly what happens essentially here. Up to this point, you're following the correct global minimum, but then you're losing it. You're only following a local minimum. And from that point, you're out of the game. No chance to come back to the original one. And that's why you don't find a systematic improvement upon increasing the network size. So it's a problem in solving the TDVP that at some point you're following the wrong minimum. Now, what is the solution to this problem? The solution is first to recognize the following problem, that so here I have a compact notation of the of this TDVP problem that we want to solve. What we have to do in order to propagate our weights is you have to invert this matrix to get a conventional ODE. Now, what everyone finds, and we also find, is that this matrix S is not invertible. And when S is not invertible, like there's one prescription how to do it. You can use a pseudo inverse upon imposing a threshold on the singular values of this matrix. But the problem is we don't have exact knowledge about the singular values because we do Monte Carlo and there's noise everywhere. We cannot do this exactly. And the key solution to this problem is to represent the TDVP in the diagonal basis of the S matrix, which I will not go show in full detail now. So, but taking this matrix S, diagonalizing it, and representing the equation in the following form, that sigma k square is now are the singular values. These are the transformed network weights, and rho k just denotes the right-hand side that we obtain in this way of this equation. So this is, again, in a shortened version, what we obtain here. Now, remarkably, there are two key observations now. And so the first observation is, and that's somewhat at first sight maybe surprising, that although we sample like everything with Monte Carlo, when you look at the singular values as a function of time here for this 2D icing problem, you see that no matter at which scale you're looking at, the singular values don't seem to have any Monte Carlo noise. There seems to be no Monte Carlo error on those, independent on the magnitude of the singular values, implying in the end that the signal to noise ratio for the singular values is only dependent on the Monte Carlo noise, and does not depend on the strength or on the signal of the singular value itself. That's good news. So we don't have to worry about the singular values themselves. However, when you look at the right-hand side, the situation is completely different. And what is shown here is an example of the signal to noise ratio in Monte Carlo by sampling the above equation with Monte Carlo for a particular point in time and a particular system size, where this rho k, all of these rho k's are plotted as a function of their index, or the whole vector rho k is plotted here. And you can see that there are many of these elements rho which have a very low signal to noise ratio, and only a few which have a large signal to noise ratio. So for the right hand side, there's a signal to noise ratio varying over orders of magnitude, and you can even predict the individual signal to noise ratio by some analytical estimate, which agrees perfectly, almost perfectly, with the exact numerics. And what this tells you is it doesn't make sense to sample all those elements down here, because they are anyway just noise that come from Monte Carlo. It's only the part up here which whose results you can trust using your Monte Carlo simulation. And what we therefore propose is a regularization scheme for this matrix inversion, which is not based on the singular values and putting a threshold on the singular values, but rather putting a threshold on the signal to noise ratio here. Now, of course, like upon increasing number of Monte Carlo samples, you can increase the signal to noise ratio as you will, and therefore this regularization scheme is completely controlled and can be systematically improved by increasing the number of Monte Carlo samples.
Sorry, I was dragged away, but you have 4 more minutes, more or less.
Yes, yes. And I'm almost done now. Here again, that's what we then obtain finally. we have also studied different kind of quenches, and we're studying like collapse and revival oscillations of the long-range order in the 2D Ising model. I will not go much into the detail here. Overall, I hope I could convince you that these neural networks are a promising approach doing non-equilibrium dynamics in 2D. And I try to highlight where are the problems and where is the potential solutions. And what I would like to just remark is that currently still the size of the network is not the limiting factor here. It's still some other instabilities that we are facing, which are limiting the timescales that we can reach. But maybe as a kind of outlook and to motivate you further that this is really a promising approach, we are currently, for instance, also studying Kibbe-Zurek mechanism in 2 spatial dimensions. And here we are together with Marek Grams and Jacek Diamaga, comparing also MPS and neural network simulations. And what you can see here is like crosses are MPS data and circles neural network data. We can reach much, much larger systems and times for the neural nets, and can observe nice scaling as expected for the Kibbe-Zurek mechanism. So I hope there's a lot of room for yet inaccessible regimes with neural nets. And with this, I would like to end my talk. And thanks a lot for listening.